Alright, so hopefully you all know about the trig identities, but I will review them really quick just because we're going to be using them in trig substitution. So the first one is 1 minus sine squared theta equals cosine squared theta. Then there is tan squared theta plus 1 equals secant squared theta, and then there's secant squared theta minus 1 equals tan squared theta. So write these down now because we're going to need them later on in the problems. Alright, cut. Okay, so we can, to use this in trig substitution, there are a few key patterns that you can look for, and these are the key patterns. Each of these patterns corresponds to a different trig substitution. So if you have any number minus an x squared, you can substitute it as 1 minus sine squared theta equals cosine squared theta. If you have x squared minus a number, you can substitute as secant squared theta minus 1 equals tan squared theta. If you have x squared plus a number, or a number plus x squared, it doesn't really matter because it's addition, you can substitute it as tan squared theta plus 1 equals secant squared theta. Now, this will make more sense as we go along, but just remember that each of these corresponds with a trig substitution. Now, another kind of key to look for is if any of this is underneath a square root sign. So if you have a minus x squared under a square root sign, it works exactly the same way as like this. So either look for that pattern or that pattern under a square root, and that usually should tell you that you need to use some trig substitution. So this is an example of a problem to use trig substitution on. There's no obvious u substitution because there's no u and u prime, and there's not really much else you can do with this problem, and it looks pretty intimidating. But the key is to look for those key patterns, and this is the first pattern, the one that is 1 minus sine squared theta equals cosine squared theta. So what we would do is go in and start setting some things equal to each other. So the first step is to set x squared equal to 9 sine squared theta. And the reason it's 9 sine squared theta is because we need to be able to factor out a 9 from the square root. So if we plug this back in, we would get the square root of 9 minus 9 sine squared theta, factor out a 9, and then we would just be left with 1 minus sine squared theta, which is the pattern we're looking for. So remember, always set, you can change the sign around any way you want to make sure that the a and the x coefficients are equal, and you can factor them all out. Okay, so then we have to square root it, and we get x equals 3 sine theta. And there's one more substitution we need to figure out, and that's the dx. So we have to derive this, and we get dx equals 3 cosine theta. So those are all the substitutions that we need to solve this problem. So the next step is to plug everything we know over here back into the problem. So if we do that, it ends up looking like the integral of 3 cosine theta, that's the dx, over 9 sine squared theta times the square root of 9 minus sine squared 9. That's a 9, don't worry. So remember, if we have to factor out the 9s from the square root, so we end up with the integral of 3 cosine theta over 9 sine squared theta times 3 square root 1 minus sine squared theta. Now, we can take this value and we can plug in cosine squared theta into that, because remember, 1 minus sine squared theta equals cosine squared theta. So we end up with 3 cos theta over 9 sine squared theta times 3, and then the square root of cosine squared theta is just cosine. So, well, I'll do some erasing real fast. Hope you wrote this down. So this becomes the integral of 3 cosine theta over 9 sine squared theta times 3. Take the square root of a square and you just get cosine theta. So this cancels out, and you get the integral of 9 sine squared theta. You can just take the 1/9 out because it's integration, and you can do that. Will said so. So you get 1/9 times, and then 1 over sine squared is basically the reciprocal. So that will be equal to cosecant squared. So you have 1/9 times the integral of cosecant squared theta. And when you integrate cosecant squared theta, you end up with 1/9 times cotangent theta. So this is part of your answer. This isn't the final step, and we will get to that in a second. Okay, so this is our answer from the last problem. I forgot to add on the C. Never forget your C's. That was bad. So what we have to do now is take it from a trigonometric equation that's in terms of theta and take it back to in terms of x. And so that's fairly simple to do, and the way you do that is just using some fairly basic trigonometry. So at the start of the equation, we said that x was equal to 3 sine theta. That was one of our substitutions. We got it from, remember we said x squared equals 9 sine squared theta, and we just took the square root of it. What we need to find here is isolate the sine, so we can plug it back into a triangle and solve. So if we divide both sides by 3, we get sine theta equals x over 3. Now remember that sine is equal to opposite over hypotenuse, so if we draw out our right triangle, set this as theta, then it would be x and 3. And we need to find this side. So using the Pythagorean theorem of, and if we set this to a, of a squared plus x squared equals 9, and then we isolate the a squared, equals 9 minus x squared, and that becomes a equals the square root of 9 minus x squared. So this side stops being a and becomes the square root of 9 minus x squared. So then we know that the final answer is equal to cotangent theta plus c. So cotangent is equal to adjacent over opposite. So we know that this is the adjacent and this is the opposite. So if we write our final answer, it would be 1 over 9 times the square root of 9 minus x squared, that's the adjacent to theta, over x, that's the opposite, plus c. So this is your final answer, going from regular algebra to trigonometry and back to regular algebra and integrating.